Young University. He was a postdoc at the National Research University High School of Economics in Moscow from September 2020 to August 2021 and has been a postdoc in Calgary University since September 2021. Dr. Nim has studied and researched on topics of quantum optical state discrimination for the quantum communication and the theory of open quantum systems for the implementation of a physical qubit. And today his talk will be about quantum communication protocol beyond the standard quantum limit. So let's just welcome Dr. Min.
Okay, thank you. Okay, hello, I'm Min Nankung from Calgary University, and I appreciate everyone attending this seminar. So I'm today talk about the quantum communication protocol beyond standard quantum limit, which includes some results of the joint work with Jong-san Kim at the Calgary University. So let's start it. First of all, I would like to tell you the things that will be presented in the seminar. Firstly, I would like to introduce the concept of quantum communication and some terms of quantum communication protocol, which was proposed until now. And then I would like to tell you about the atomic indirect measurement, which is the measurement based on the atom, and which can be used for binary quantum communication, and propose that the performance of the protocol can be improved by choosing some kind of quantum light as a signal. Finally, I would like to conclude this seminar and provide you the future work corresponding to the contents of this seminar. First of all, let me suppose that Alice prepares one bit message X and sends it to Bob. Then the most easiest way for the Alice would be just to write the X in the letter and send it to the Bob by the post officer. Then Bob can just distinguish the message by just opening the envelope and read the X. In this case, it is trivial that the success probability for Bob correctly distinguish the Alice message would be the 100% or 1. The problem is that if the distance between Alice and Bob is not too short, then it could take several days, or in the worst case, it would be the several months. So to fix the problem, Alice can prepare the message and include the message X into the right plus UXT, which means that UXT is the right plus and it is the time-varying function. Then to distinguish X, Bob also needs to perform the measurement so as to decode the X included in the light pulse. So there are some kinds of the conventional measurement, which includes on-off measurement and homodynamic measurement. First of all, I will introduce the on-off measurement. It is the simple. So Bob's outcome would be click or non-click. If click, it means the pulse exists between Alice and Bob. If there is no click, it means no pulse between two of them. So if Bob obtains the outcome, which is the click, then Bob decided that Alice prepared the message 0, and the otherwise Bob decided that Alice prepared the message 1. The other thing is the homodynamic measurement. It is a little bit complicated, so let me briefly introduce the structure. Okay, so if Alice prepares the right pulse UXT, then Bob also can prepare the beam splitter and local oscillator. So in the local oscillator, another kind of light is generated. And then in the beam splitter, both the signal from Alice and another light from the local oscillator interacts and propagates to the photodiode 1 and photodiode 2. And according to the photoelectric effect, the photoelectric current I1 and I2 happens from the photodiode 1 and 2. And someone can use such as op-amp or other kinds of electric devices to construct the current subtractor. In here, Bob can calculate the difference between I1 and I2. So in this case, if the I1 minus I2 is larger than or equal to 0, then he decides that Alice prepares the message 0, and otherwise the Bob can decide that Alice prepares the message 1. So, okay, I would like to note the one thing. That is the success probability. If the Bob uses the conventional measurement, then it cannot surpass some upper bound. It is so-called the standard quantum limit. I can tell you there's the two reasons for this. The first one is that the light, which Alice uses for the information carrier, has the limited statistical properties, and the other one is that the measurement proposed by Bob it also has the limited physical structure. The two reasons makes the success probability of these conventional measurements cannot surpass the so-called standard quantum limit. Okay, so meanwhile, according to the quantum theory, such standard quantum limit can be surpassed. So that is why the quantum theory can be used as for the designing quantum communication which can surpass the SQL. So in this case, the success probability for the communication can be derived as follows. Here the Q0 and Q are the prior probabilities that Alice prepares psi0 and psi1. Here, instead of using the light pulse, Alice can prepare the pure state of psi x to encode the Alice message x. So in this case, Bob's measurement can be described as the POVM whose elements is given pi 0 and pi 1. So the maximum success probability can be expressed as the optimum of this average success probability over all possible POVMs. So this is so-called Astron bound. And it is well known that for some fixed or pure or some quantum states, it is the success probability, it is the error probability. So according to, it is well known that the error probability by the standard quantum limit is larger than the Astron bound. This means that by using the quantum measurement or so-called unconventional measurement, the error probability can be minimized more than the conventional measurement, including homodyne or on-off measurement. So the main purpose of our research is as follows. First one, designing unconventional measurement, which can surpass the SQL. The other one is to design an unconventional measurement, which can achieve the Astron bound, which is defined as follows. So, okay. Now I will tell you about the process about the quantum communication and arise some questions regarding the processes. First, Alice can prepare the message. I call it message preparation. Here, Alice prepares a message X, which is 1, 2, 3, or n in general, and encoding X to some quantum state, which is psi X or rho X, where rho X that's the operator. So then Bob can perform the measurement so as to obtain the outcome. Here I consider that outcome is also be 1, 2, 3, or n. And based on the measurement outcome, Bob can decide which X Alice have prepared. So I will focus on the two parts of the entire quantum communication. First one is the encoding and the second one is measurement. I will consider the measurement first. So how much the figure of merit can be optimized. Here, the figure of merit can be considered as the success probability or equivalently error probability, or the amount of information shared by Alice and Bob through the communication scheme. And the second one is to optimize the figure of merit, how the measurement can be designed in terms of quantum optics or other physics. And the part of the encoding, I will tell you like this. which quantum state of light can be used as the information carrier, or how such the quantum state of light can be used for improving the Hedstrom bound. Then the other one is how can which noise between Alice and Bob can be considered in the quantum channel for the practical quantum communication. So based on these kinds of questions, I will tell you some kinds of proposals in the next slide. So first of all, I will tell you about the unconventional measurements which have been frequently used. I think the unconventional measurements which were frequently used until now can be classified as two kinds. First one is the Kennedy receiver, which includes displacement operation and on-off detection. And the same as the Dolina receiver, which includes also displacement operation and on-off detection. The main difference between these kinds of receiver is that it contains the electric feedback, but it does not. So that is some kinds of frequently used conventional measurement. Then the other one is the frequently used quantum optical state for the information carrier. Until now, so-called Glauber-Schlusston coherent state, or simply the coherent state, have been used for the information carrier because it can be easily generated by using the laser technique. So here, in the mathematical expression, alpha is given as the complex amplitude, and the absolute value of the alpha is amplitude. And since it is the complex number, it contains exponential of I pi, and pi is the pace. And also, n means the number of photons, so the cat expression of the n is the photon number state, or equivalently, it is defined as the Fock state. So, okay, here I told you that the Kennedy receiver and Dolina receiver contains the displacement operation and on-off detection. So in mathematics, displacement operation is expressed as a unitary operator, which is so-called displacement operator, which is defined as follows. Here, A nega is so-called creation operator, and A is the annihilation operator. Here also, gamma is a complex number in general. So why this is the displacement operator? The reason is as follows. Suppose that a coherent state is acted by the displacement operator, then the displacement operator transfers the coherent state alpha to the other coherent state gamma plus alpha. That is why it is so-called displacement operator. The other one is the on-off detector. It only detects the on and off. The on means that there is at least one photon, and the off means that there is no photon. So in mathematics, the pi off and pi on can be expressed in terms of the Fock basis. Here, 0 means no photon, and 1, 2, 3 means there is at least one photon. So, okay, in the Kennedy receiver, Alice prepares the signal, the alpha x, where the x is the encoded message, and then Bob also prepares the beam splitter and the local oscillator, and the signal from Alice and another light from the local oscillator interacts in the beam splitter, and the whole process, including the beam splitter and the local oscillator, is expressed as just the displacement operator. So after the displacement operation, then here the minus alpha 0, then Alice signal is transformed into the coherent state with alpha x minus alpha 0. Then suppose that Bob can prepare an ideal on-off detector. Okay, so if Alice prepares the message 0, then it becomes 0, which means there is no photon inside there. So Bob can choose that Alice have prepared the alpha 0 and the message x is equal to 0. And if Alice prepares the message x is equal to 1, then you can see that this becomes alpha 0 and alpha 1, and this value cannot be 0, which means there is at least one photon. So if Bob's outcome is on, then it means Bob can decide that Alice can decide that Alice prepared the x which is equal to 1. So in this case, the average success probability according to the Kennedy receiver is given as follows, and according to this, according to this, the error probability is it cannot be lower than the Hellstrom bound, but it is well known that it can be lower than the standard quantum limit. So the other idea is to, instead of using the fixed displacement operator, suppose that the displacement operator can be controlled. Then I think the gamma here can be controlled. Then the error probability can be minimized with respect to the gamma, or here is the success probability. The maximizing the success probability over the gamma is equal to the minimizing the error probability over every gamma, which is in the complex number. So in this case, the error probability can be lowered more than the original Kennedy receiver. Then still there is some difference between the minimum error probability over every gamma with the Hellstrom bound. So we had to, so it is needed to shorten the difference between the receiver and the Hellstrom bound. So according to the Doliner, which was proposed in 1973, okay, let me see. Okay, by using the such electric feedback, Doliner showed that this kinds of the receiver can achieve the Hellstrom bound. So here the alpha x is listed as the following kinds of the coherent states, and at 1, 2, 3, and n means the order passed through the beam splitter of the Bob. So suppose that n slice of the coherent state passes the beam splitter, then Bob also performs the displacement operator by using the beam splitter and the local oscillator. And then Bob would perform the on-off detector, and he would get some outcome. And the outcome is used as follows. In case of the n is equal to 1, 2, and n minus 1, then the measurement outcome is used for the updating the displacement operator for the discriminating the n plus 1 slice. And in case of n, which is equal to n, large n, this means that the slice is the last order for the transmission. Then the measurement outcome is used for discriminating or deciding which coherent state Alice prepared, or which message Alice had prepared and encoded in the coherent state. So it was okay because it could achieve the Hellstrom bound. The problem is that it needs real-time electric feedback, which is very difficult to be implemented in the experiment or the practical quantum communication. So as I told you here, it contains real-time feedback in order to achieve the Hellstrom bound. So instead of using the real-time electric feedback, I and Jung-san considered another kind of the measurement, which is so-called atomic indirect measurement. That is because it can nearly achieve the Hellstrom bound without the real-time electric feedback. So let me introduce the atomic indirect measurement. Suppose that Alice prepares the rho x, which is the density operator including the message X and sends it to Bob. And then Bob can also prepare his auxiliary state sigma. And then after the preparation, Bob can perform some kind of unitary operator between the state prepared by Alice and the auxiliary state. Then after the interaction by the unitary operator, Bob can perform the projective measurement. That is the whole process of the indirect measurement, and each element is contained in the statistical realization. Here, let me explain the elements in the statistical realization in detail. Here, the sigma is given by the ground state of the atom. I and Jongsan consider the two-level atom which has the ground state and the excited state. So the other thing is the projective measurement, which is defined as follows. Here, pi 0 and pi 1 are the vectors, which is linear combination between the ground state and the excited state. And it is easy to show that the pi 0 and pi 1 are orthogonal to each other. That is why these two kinds of the projector constructs the projective measurement. And then this part is the most important thing for the atomic indirect measurement. Let me explain this part more slower. To design the U, it was needed to consider the Hamiltonian, which describes the interaction between atom and light. Here, the rho x can be considered as the quantum state of light. So according to the James-Cummings model, the interaction between the atom and the light can be described as follows. It is solely because of the physics. So the first part, a tensor product sigma plus this, means the situation that the level of the atom arises from the ground state to the excited state because of the annihilation of one photon. So if one photon is vanished, then the energy happens. Then because of this energy, the atom arises from the ground state to the excited state. And the second term means that suppose that the atom becomes excited state to the ground state, then it would obtain some energy, and this energy can create a new photon. That is the meaning of the second term. So we have the James-Cummings, we have the interaction Hamiltonian based on the James-Cummings model, and by using the interaction Hamiltonian, we can obtain the unitary operator tilde ut, which is based on the time-dependent Schrödinger equation, and it was possible to analytically solve the Schrödinger equation, and the solution is given by this. Here, the tilde omega means the time-dependent interaction strength between light and atom, and the tilde omega is included in the pi tilde as like this. So suppose that interaction happens between the time period large t, then the tilde u of large t becomes the u in the statistical realization. So we are ready to consider every part of the atomic indirect measurement. And according to the previous result, such kinds of the atomic indirect measurement can achieve the Hellstrom bound like this if Alice prepares one out of ideal coherent state. Ideal coherent state means that the coherent state does not include any noise. In this graph, we can just focus on the black line, green line, and red line. Here, the x-axis means the mean photon number inside the coherent state, and the y-axis is the error probability. Here, the black line means the standard quantum limit, green line means the success probability optimized according to the atomic indirect measurement, and the red line means the Hedstrom bound. So, according to this result, standard quantum limit can be surpassed by the atomic indirect measurement, and it can also nearly achieve the Hedstrom bound if the mean photon number is not so large. That means that I think this is important because the atomic indirect measurement does not include any real-time feedback. Even without this feedback, it can surpass the standard quantum limit and nearly achieve the Hedstrom bound. So the problem is that this is only for the ideal case, which means there is no noise contained on the coherent state. And to consider the practical quantum communication, the noise between Alice and Bob is needed. So we considered the phase diffusion noise between Alice and Bob, which is mathematically defined as the following quantum channel. And by applying some ideal coherent state alpha x into this quantum map, then we can obtain the tau x. And tau x becomes like this. And you can understand the meaning by focusing on this exponential part. This part means the Gaussian distribution. Before the phase diffusion noise, we can understand that alpha x, which is ideal one, has fixed phase, but because of the phase diffusion noise, the phase has some distribution like Gaussian, which means there is uncertainty, which is happened by the phase diffusion noise. So, okay, to consider the performance of the atomic indirect measurement under the phase diffusion noise, we compared with the other kinds of the feedback excluded receiver, which was proposed in the 2019 in MPJ Quantum Information. So here, Alice prepares the signal alpha x, which includes the message x, and sends it to Bob. Then Bob can also perform the displacement operator, and then later Bob performs photon number resolving detector instead of the on-off detector. Here, PNR M means that the resolution is equal to M. I will talk about the meaning of the resolution. So the photon number resolving detector outcomes the number of the photon, so it can be mathematically defined as like this. So here, pi 0 means the outcome of the 0 photon. This means 1 photon, 2 photon, and m minus 1 photon. And the other thing is defined as the pi m, which means that if the number of photon is observed more than or equal to m, it can be considered as just one result. That is why such measurement is so-called the photon number resolving detector. Here we have n kinds of the outcome. So based on the outcome, Bob can choose the Alice message by using the maximum posteriori decision rule. Here, Bob can calculate the conditional probability between k bar a0 and k bar a1. If this conditional probability is larger than or equal to this, then the Bob's outcome is Bob decided Alice prepared the 0, and otherwise the Bob decided that Alice have prepared the message 0 and message 1. So we compared the minimum error probability between the atomic indirect measurement and the feedback excluded receiver, which was proposed before. So in this graph, we consider the BPSK. The BPSK means here is the signal, and the signal is given by the plus alpha and minus alpha, where the alpha is the real number. That is the definition of the BPSK. Then OOK is the on of K, which means the 0 and alpha. So 0 means the off and alpha means the on. That is why it is called on of key. So in the case of BPSK, whose average photon number is given by the 0.5, then the graph is given by the like this. Here, the solid red line means the minimum error probability of the atomic indirect measurement, and the dashed blank line means the feedback excluded receiver, which is defined as follows with the resolution number is equal to m is equal to 1, and the blue one is the Hestrom bound. According to our result, we could show that the atomic indirect measurement can nearly achieve the Hestrom bound, and it could be closer to the Hestrom bound more than the feedback excluded receiver for any regions of the sigma. Sigma is the standard deviation of the phase diffusion noise. So this is the case for the BPSK, and this is the case for on-off key. In this case, we show that the red solid line is larger than the Hestrom bound, even larger than the dashed blank line, which means that the atomic indirect measurement cannot be outperformed by the feedback excluded receiver. So we have concluded that the atomic indirect measurement is useful for the BPSK case. So we have focused on the case of such BPSK. So we have considered also that average photon number is equal to 0.75, and in this case the dashed blank lines means the feedback excluded receiver with the resolution in number is 1 and 2, 3. According to this case, we could also show that the atomic indirect measurement, which is depicted in the red line, can be closer to the Hestrom bound more than the feedback excluded receiver with the resolution number is equal to 1. And in the other case, the resolution number is 2 or 3. We could show that in the range of the sigma, which is not too large, then the atomic indirect measurement can outperform more than the feedback excluded receiver. And as well as the atomic indirect measurement could achieve the Hestrom bound in the small range of the sigma. So also the other thing of the figure of merit is considered as the accessible information. Here IAB means the Shannon mutual information, which means it quantifies the shared information between Alice and Bob, and it can be maximized over all possible measurement performed by Bob. That is defined as the accessible information. So we also consider the accessible information, and here the red line means the atomic indirect measurement, and blue line means the Hestrom bound. And also and dashed red line, and here means the resolution rate with 1, 2, 3. And according to this result, by using the atomic indirect measurement, Alice and Bob can share more information compared by such kinds of the feedback excluded receiver, which if the standard deviation of the phase diffusion is not too large. Also, it could achieve the accessible information, which is depicted as the solid blue line. This means that not only the Hellstrom bound, the atomic indirect measurement can also achieve the mutual accessible information, even if the channel between Alice and Bob is exposed under the phase diffusion noise. And now I will talk about how the performance of the protocol can be improved by choosing some kind of quantum state of light. Before that, we have considered the on-off keying signal and binary phase shift keying signal, so as to send 1 bit for a single pulse at most. But if we consider the N-ary phase shift keying, which can be also called as NPSK, it can transmit log 2 of m bit per a single pulse at most. So that is why the N-ary phase shift keying can be also considered. So the problem is that how the Hellstrom bound can be improved, which means that the Hellstrom bound can be minimized such that the error probability guaranteed by the quantum measurement can be lowered. I think there is the two kinds of the method. The first one is by considering the squeezing operation, which is equal to the generation of the displaced squeezed state. So coherent state is what I told you in the previous slide, and I will talk about the squeezed state in the current slide. So squeezed state is mathematically defined as follows, with the z is equal to the complex number defined as follows. So according to the quantum theory, the coherent state can be generated by acting the displacement operator on the vacuum state, and also the squeeze state can be obtained by applying the squeezing operator, which is defined as follows on the vacuum state. So suppose that we can hybridize the displacement operator and squeezing operator. So first of all, here is the vacuum state, and after the displacement operator, then the zero becomes the coherent state. And after that, someone can perform the squeezing operator, then we can obtain the such like this. So this is so-called squeezed and displaced state. So there was some result according to some textbook that by using the squeezing operation, the minimum error probability can be lowered. Here, first one, I will consider the BPSK. Here, this part is the squeezed displaced state, and this case is for the coherent state. According to this graph, then the minimum error probability, or equal to the Hellstrom bound, can be lowered if we choose the squeezed displaced state as an information carrier instead of the coherent state. And same thing happens for the 4PSK, which means that it can transmit 2 bits per single pulse. In this case, it can be observed that the squeezed displaced state can lower the Hellstrom bound or minimum error probability more than the coherent state. Okay. So the other idea for lowering the Hellstrom bound or improving the performance of protocol is the generalization of the Glauber-Stephenson coherent state. The Glauber-Stephenson coherent state is defined as follows, and here is the typo, where the alpha is equal to, alpha is the complex number. So in this case, we can consider the photon statics, and the probability that the photon number is equal to n becomes the Poisson distribution. So the idea is to generalize the statistics about the photon number as follows. Here, alpha over n is same, but the difference is that the other thing becomes the hn, which is the real valued function. And then we can obtain that the probability for the photon number is also generalized as follows. So here, as I told you, the Hn is the real valued function, and so we have infinite numbers of the Hn. So I can define H vector, which means the tuple of real valued function, and the real valued function which from 0 to r square to some real value, which satisfy these three kinds of conditions. The reason for considering these kinds of conditions is as follows. The first one happens because that this coherent state should be normalized. The second one means that the mean number of the mean photon number according to the quantum theory should be equal to that of the statistical theory. That is why the second condition comes. The other inequality comes. That is because of the resolution of the identity, which is one of the well-known conditions in the quantum optics. And here, this coherent state is so-called non-standard coherent state. So there is some physical property which would be important for understanding the non-standard coherent state. So according to the Glauber-Stetson coherent state, this is known as the Poissonian, which means the statistical property has the Poissonian. So it can be quantified as so-called Mendel parameter. Okay, so in this Mendel parameter, the Glauber-Stetson coherent state has the 0 Mendel parameter value. This means that the Glauber-Stetson coherent state is Poissonian. And we can consider that the value of the Mendel parameter is lower than 0 or larger than 0. The former case is the sub-Poissonian and the other case is the super-Poissonian. So in case of sub-Poissonian, such as optical spin coherent state, Baruch-G-Larudel coherent state, and modified subsequent coherent state can be considered as the sub-Poissonian, and Perelomov coherent state can be considered as the super-Poissonian. So,
sorry, 15 minutes left.
Excuse me?
15 minutes left.
15 minutes left. Okay, thank you. And okay, the reason for considering that such physical properties is that it can be related with the performance of the quantum communication. Let me briefly introduce, but it seems that there is no time, so I will pass this part. So just a moment, please. Okay, I think I need to explain this part. According to the previous result, on-off keying signal composed of the optical spin coherent states and the Perelomov coherent states are considered. In these graphs, the blue lines correspond to the Glauber-Stetson coherent state, and the other colored lines are, in this case, optical spin coherent state with different parameters, and here the colored line means the parallel coherent states with different parameters. So in the first of the graph, then it could be shown that the Hellstrom bound can be lowered if the optical spin coherent state is used instead of the Glauber-Stetson coherent state. In other words, the parallel coherent state, by using this coherent state, the Hellstrom bound cannot be lowered more than the Hellstrom bound of the Glauber-Stetson coherent state. So as I told you, the optical spin coherent state is the sub-Poissonian, and the parallel coherent state is the super-Poissonian. So this result means that the sub-Poissonian can be helpful for lowering the Hestron bound or improving the performance of the protocol, but super-Poissonianity cannot be useful for improving the quantum communication. So, so that would be the evidence. So our recent result is right as follows. Instead of the on-off keying signal, we consider the BPSK signal. That is because we understood in the previous result that the atomic indirect measurement is very useful in case of the BPSK signal. So we consider the BPSK signal composed of the optical spin coherent signal. Here, the x-axis means the mean photon number and y-axis means the success probability. And the solid red line here means the Hestron bound improved by the optical spin coherent state. And just a moment, please. And the blue one is the optical. The solid red line means the optical spin coherent state. Hestron bound of the optical spin coherent state, and stars means the maximal success probability, which is maximized over all possible atomic indirect measurement. So, according to our result, the atomic indirect measurement, which was optimized, can achieve the Hestron bound, which is improved by choosing the optical spin coherent state. So, although there are lots of sub-Poissonian coherent states such as optical spin coherent state, BGCS, and Susskind global coherent state, and we have considered all kinds of things, but we just focused on showing the case of optical spin coherent state because I thought it could be more good for making the graph more larger, so it can be easily observed. And the other one is for the general case that NPSK signal is considered. And in mathematics, NPSK signal can be described as the set of such coherent state. And here the alpha x given by such the exponential. Then according to the theorem 1 of our result in this paper, and there exists a unitary operator v tilde such like this, where the v x tilde is the unitary operator, satisfying that the tilde v over n times n is equal to identity. And based on the theorem 1, and we could analytically derive the Hestron bound in case of the n-ary general PSK signal as like this. So by using the analytical result, we could investigate the Hestron bound between BGCS and parallel coherent state and the Grabo-Stetson coherent state. In these two graphs, especially in here, the solid line means the I'm sorry, just a moment, please. It seems that this graph should be changed. So, so this is the case for the parallel coherent state, and this is for the Barlow-Girardello coherent state. So, Okay, I'm sorry for confusing. So this is for the Barth-Giraldet coherent state. The second one is for the Pananomov coherent state. So according to the first result, the solid line is the Hedstrom bound by the Glauber-Stephenson coherent state with composing 8 PSK signal, and the other colored lines correspond to the Barth-Giraldet coherent state. In this case, the solid one means the Hedstrom bound of the Glauber-Stephenson coherent state, and the other colored lines correspond to the parallel coherent state. According to the first result, it can be shown that by choosing the BGCS, it cannot be lowered more than the Hedstrom bound. Meanwhile, by using the parallel coherent state, it can be lowered more than the Hedstrom bound. And let me go to the slide back. So in this case, according to this result, the sub-Poissonian coherent state can be considered as the improving the performance of the protocol, and the super-Poissonianity cannot be used for improving the performance of the protocol. And I think if the number of the coherent state is larger than 2, that it could happen the different thing. In this case, the Barth-Giraldet coherent state, which is understood as the sub-Poissonian, cannot improve the performance of the protocol. Meanwhile, the parallel coherent state with composing 8 PSK signal can improve the Hedstrom bound more than the Glauber-Stephenson coherent state. So that would be difference between the case of BPSK and the APSK. So, okay, this is the conclusion of the seminar. So we have shown that the atomic indirect measurement nearly achieves the Hedstrom bound as the accessible information. Even the channel between Alice and Bob is exposed to the phase diffusion noise. The second one is that the atomic indirect measurement can outperform the other kinds of the Kennedy receiver, which is so-called feedback excluded receiver, composed of the photon number resolving detector and the maximum posteriori decision rule. The third one, the atomic indirect measurement, can nearly achieve the Hedstrom bound improved by the binary sub-Poissonian coherent state. And the fourth is that unlike the binary case, if the number of the coherent state inside the PSK signal is larger than 2, then there is some cases that the sub-Poissonianity cannot be helpful improving the performance of the protocol, and even the non-standard, even the super-Poissonian coherent state can be helpful for lowering the Hedstrom bound. And the future work, considering the future work, we would like to consider designing the indirect measurement for quantum communication with n-ary coherent states, because we have considered for the binary cases, and we would like also consider investigating the optimality of indirect measurement with n-ary signal under the noises such as phase diffusion or the other such as thermal noise, which is also well known. And third, we would like to consider the phase diffusion and thermal noise and how such the noises can be reduced by some operations such as the squeezing operation. And the last one is, until this seminar we have considered that the Alice and Bob performs the communication to each other, and so I think we could think that since the indirect measurement does not completely destroy the information contained in the Alice state, so we think that it can be used for designing multiple quantum communication between sender and the multiple receivers. Okay, and thank you very much.
So thank you for Dr. Kim. mandatory. So if anyone has any questions.
Yeah, I wanted to know how, if at all, this work has any implications on quantum communication when you encode information in the polarization states of photons.
Okay, that would be the good question. Let me go to the previous slide. Okay. It seems that you're asking that how the difference of how the change of the photon statistics can lower the Heston bound. Is it right?
No, not using different coherent states, but rather encoding information in polarization, like horizontal versus vertical polarization, like we often do in QKD protocols that we implement. So does your theory make any predictions about that kind of communication and error bounds on those kind of communications?
Yes, that would be a good question. So, suppose, yes, it could be considered for single photon with horizontal or vertical states. So, for the sending some message, the problem is that if it contains only one photon, and it would not be robust under the noise if we use the vertical or coherent, vertical or horizontal single photon state. So we consider the kind of coherent state and skew state, which are so-called continuous variable quantum states. That is because it contains many numbers of the light, and it would be robust under the noise peak, even if some photons are affected by the noises. That is the reason why we have considered such light. Thank you.
So anyone has any other question? So if not, then let's all thank the crewmen. And thank you for the talk.